Okay. Now I'm going to share my screen. 1 second. All right. So welcome to our August PEP Talk, which will be led by Warren M. Ewert. He retired not too long ago as senior fellow from Phillips 66, which I'm sure all of you know, but it's an American multinational energy company. At Phillips 66, he took on a plethora of different roles, including chief technical advisor and mentor to the Phillips 66 technology organization. And just a little bit about his background in schooling. He obtained his MS in chemical engineering from Kansas State University in 1980. And he received his MS in chemistry from Oklahoma State University in 1988. So Warren is very experienced. He has over 35 years of experience in petroleum and petrochemical R&D. Again, thank you so much for attending today's PEP Talk. So just to give you a little bit on the agenda, we're going to be talking about the background of the PEP Talks, which Scott will walk you through a little bit. And then after that will be Warren's presentation. And we'll leave about 20 minutes or so for discussion. So please, as you're listening to his presentation, make sure that you jot down any questions that come up so you can ask them during the discussion. And then afterwards, I'll talk a little bit about the upcoming PEP Talks. All right, Scott, I'll pass it over to you.
Great, thank you, Danica. I'm not going to read the words on the screen, but suffice it to say that we are forming a community of process engineers, and this PEP Talk series, or Process Engineer Perspective series of talks, is really all about providing a venue for process engineers to gather and to talk about issues of interest that they all have.
Everyone, can you please make sure you're muted, please? Thank you.
In any case, the community of process engineers is proud to present this as an initial offering of what the community is going to be all about. We are hopefully finalizing the governance documents of the community, and so stay tuned. There will be more to report the next time we get together. So with that, I will turn it back over to Danica.
Okay, thank you so much, Scott. So today, as you know, Warren will be discussing purity and composition issues in chemical manufacturing and crude oil refining. So Warren, thank you again so much for agreeing to lead this PEP Talk. It was a little bit short notice, but we're all very much looking forward to it. And I'll stop sharing my screen right now and I'll let you take it away.
I'm going to go ahead and turn my video off just to maybe improve the bandwidth on my end, and I'll share my screen here.
Okay, let me know if you're able to share or not. I think you should be good.
Yep.
Okay, perfect.
Hopefully go into the presentation mode and hopefully everyone can see the slides.
Can everyone see the slides?
Yeah.
All right, perfect.
Yes.
Okay. As Danica said, I spent 35 years in R&D for Phillips Petroleum, ConocoPhillips, and Phillips 66. But I served at the interface of process development and scale up, where I was actually involved in the commercialization of a number of different processes and products. And today I want to share some common threads related to the issues of purity and composition, all the way from a very highly specialty chemical type of application all the way to crude oil refining. And so we're going to cover a lot of space, and maybe some of this area is familiar to various listeners, and maybe some of it is brand new, but I hope it's of interest and entertaining to you in some capacity. So just a quick history review from Phillips Petroleum all the way to Phillips 66. The names look familiar, but it's actually a journey of different corporations. Phillips Petroleum was founded way back in 1917 here in Northeast Oklahoma in Bartlesville. It's a little town about 45 miles north of Tulsa. And it was a fully integrated oil company, all the way from oil and gas exploration and production, natural gas processing, all the way to crude oil refining, transportation, and marketing. And I'm sure that many of you have seen the Phillips 66 gas stations if you've ever traveled through the Midwest, which was their primary marketing area. In 2000, based on their mutual interest in the area of specialty chemicals and olefins and polymers, Chevron and Phillips Petroleum Company formed a 50-50 joint venture called CPChem, where they brought those portions of their business together. And that entity has existed now for over 20 years with a focus on producing olefins as well as polymers and specialty chemicals. In 2002, following the rest of the oil industry, there was consolidation where Conoco and Phillips Petroleum joined together to form ConocoPhillips. And again, this was a fully integrated oil company, all the way from oil and gas exploration and production to refining and marketing. And then finally, 10 years later in 2012, based on an analysis of the value of our stock in the marketplace, ConocoPhillips decided to form two entities. One became the upstream entity that continues to bear the ConocoPhillips name and is focused primarily on oil and gas exploration and production. And then a new company, Phillips 66, which split out and is focused merely on the refining, transportation, and marketing aspects. The 50% interest in CPChem that was held under ConocoPhillips went to the Phillips 66 company. So that's kind of a corporate history. It turns out that their major R&D center located here in Bartlesville, Oklahoma, remained the same even with all this alphabet soup of name change. And so my career covered all three of these various entities. So that's my background. So going back for some history, back in the early 60s, with their interest in the natural gas that was being produced at some of their facilities, Phillips, along with many of the majors, was exploring the whole new realm of polymers and olefins and polymers. And out of that work came some groundbreaking work where the subject of olefin metathesis was being explored. And here you can see these researchers in the 60s were working with a process that came to be known as the Phillips triolefin process. And what we found is that you could take simple olefins and over either in a stirred tank reactor with a liquid phase catalyst or a solid phase catalyst, you could scramble those double bonds. And Phillips' interest here was to take ethylene and butenes and convert them to propylene, primarily with the interest of eventually making polypropylene, which became a major business for them, especially in the 60s, 70s, and 80s. So if we take this olefin metathesis process and we generalize it, here I've taken us back to organic chem. Hopefully everybody is familiar with these stick models of hydrocarbon structures. And if you take two olefins that may have a total of 4 different substituents around the double bond, if you pass those materials over a tungsten oxide on silica and magnesium oxide catalyst, if it's activated properly, you can actually scramble those double bonds to form 2 brand new olefins. And this opens the door to creating some new molecules that might be especially useful in the specialty chemical space. And so I've listed down below some interesting starting materials that might actually be of interest for making novel diolefins and triolefins. And so here in this example, we have cyclooctene, we have 1,5-cyclooctadiene, and then 1-butene and 1-hexene. These are all molecules of interest that we're going to talk about, especially as we get into the specialty chemical space involving insect pheromones. So to familiarize yourself or refamiliarize yourself, insect pheromones are the chemicals that insects themselves synthesize in their bodies, largely based on the ingested chemicals that they get from eating plant materials. And there's a whole wide variety of things that insect pheromones do. 2 of the most useful ones are for mating attraction, where typically the female gives off some sort of pheromone chemical and the male is attracted, or signaling, where an insect finds a viable food source and releases a pheromone that causes other insects of the same species to aggregate to attack that food source. This opens the door for a non-toxic option for insect control. If we can synthesize these same pheromones that the insects do in their bodies, if we can do that synthetically, we can potentially put those pheromones inside attractant traps and draw the insects there and trap them. either for monitoring just to see whether there's a pest infestation that's becoming a problem in a certain area. Or on a broader base, if you disperse this pheromone into the environment, you can disrupt mating by basically blanketing the natural pheromone that the females release and causing confusion such that the males really can't find the females. So it's a synthetic dispersion in the environment. A lot of these molecules potentially lend themselves to the olefin metathesis technology because many of the insect pheromones, not all of them, but many of them are simply unsaturated alkenes, alcohols, acetates, or aldehydes in the 12 to 23 carbon range. And what we find is that there's the way the insects fabricate these materials, there's typically one or more double bonds, and there's a particular cis-trans or ZE orientation that the insects are making and are responsive to when those materials are out in the environment. So this leads us with a synthesis objective that we can potentially try and meet through the use of olefin metathesis. The first one I want to talk about here and some of the challenges that we encountered is the pheromone gossipluor. It's the pheromone for the pink bollworm cotton pest, and you can see in the Latin name there, and I won't try and actually repeat that, but you can see where the term gossipluor might come from, the latter half of the Latin name for the pink bollworm. And it turns out it's a 16 carbon, duly unsaturated acetate, 7,11 hexadecadienyl acetate. When my oldest daughter was 2 years old, I tried to teach her how to say that almost as a parlor trick. And it turns out that she's now 36 and she works at the same research center where I used to, and she does chromatographic analysis. So one day she told me when she was taking organic chemistry that she said the veil had been pulled back from her eyes and she actually knew what she was talking about now when she said that term. But so again, you can see here, we've got a long molecule. It's got some double bonds in it, and it's got some functionalization at the end. And it turns out that the insect prefers a mix that's got about a 50-50 cis-trans mix at the number 11 carbon position, the 11-12 carbon position. And so I've drawn that in as a squiggly line just to indicate that we've got a mix of isomers that we're trying to target if we're going to synthesize what the insect uses. So Phillips scientists in the 1980s attacked this problem by going back to the use of metathesis. And here we have 1,5-cyclooctadiene and 1-hexene. And so if you remember, the metathesis process takes these double bonds and scrambles them. And what we were able to do over a fixed bed catalyst is synthesize this 14 carbon triene. And you can see where all the double bonds are. The one at 5,6 was originally present in the cyclooctadiene itself, but the new double bonds at the 1,2 position and the 9,10 position are the result of the metathesis. And so if we stretch that molecule out here, you can see that what we in fact produce by the metathesis process is a mix where at the 9,10 position, we have this 50-50 nominally mix of the cis-trans or the ZE configuration in that 9,10 double bond. So we're already building a molecule that has some parallels with the gossipluor that we want to try and make. But at this point, we only have 14 carbons, so we need to do a little more work. We're going to take this tetradecatriene, this long chain triolefin, and we're going to build it and expand it, and then we're going to try and functionalize it. And so it turns out that the primary double bond at the 1,2 position is especially amenable to further chemical reaction while leaving the double bond at the 5,6 and the 9,10 position alone. So what we can do, and I won't go into all the chemical details because I realize that we're mostly engineers on this call and not organic chemists, but it turns out that if you react this tetradecatriene appropriately with ethylene oxide, that allows you to build 2 more carbons on the chain. And then if you react that with the acetyl chloride, which is shown in the middle there, you can functionalize that end to make the acetate. And the end result is we successfully made the gossipluor pheromone, the 7,11 hexadecadienyl acetate. By adding the 2 carbons, we've shifted the the carbon number location for the two internal double bonds that make up gossipler. And this was described in a patent issued in 1986 to 3 Phillips researchers who were actually some of my contemporaries when I was working at the research center. So capitalizing on this success, where this molecule gossipler was previously made by a more difficult route of trying to hydrogenate acetylenes, we realized there was a market opportunity. We basically come up with a way to make this compound a lot cheaper than any of our competitors. And so in order to commercialize this, Phillips formed a joint venture with Dow Corning called AgriSense in 1988. Dow Corning brought their microencapsulation technology in polymer beads to the table, and we brought our pheromone synthesis technology. And it turns out that if you infuse those polymer beads with the gossipler pheromone, you can spray them out of an airplane just like a crop duster, and that puts them out into the environment in the cotton field, where you provide this blanket that basically confuses the male pink bollworm and they can't find the female, and the end result is effective insect control. So with this move to commercialize this process, number one, even though these materials don't kill insects, they modify their behavior such that they're regulated by the federal government just like you would an insecticide. Well, that means that you have to tell the government what the purity is going to be, and in the case of our material, what the double bond configuration is going to be, or at least the range that you intend to manufacture. And so based on the laboratory data and small pilot plant scale data that we had, we got an approved label from the government to commercialize gossipler. And of course, with our attempts to commercialize this whole process, as well as other pheromones, the result was we needed a dramatic expanse in our ability to produce the gossipler production. So in order to do that, the first thing we needed to do is we needed to come up with a way to make a lot more of this tetradecatriene intermediate. And that meant moving from a small scale fixed bed reactor to a very large pilot plant scale inside the research center. It turns out that the global market for pheromones, because they're so high value, anywhere from $1,000 to $10,000 a kilogram, the worldwide market for these materials oftentimes is less than 1,000 kilograms per year. So you can do these kind of syntheses at what might look like an R&D scale, but in fact, you're really working at commercial scale for pheromone production. Well, when we tried to scale up the tetradecatriene, all of a sudden we found that our final product fell outside our government-approved label specifications. At the 11th position, our label said we could make materials that range from a ratio of 48 to 52 all the way up to 52-48. And that was based on the laboratory experience that we had just analyzing the batches that we had made in the past. But all of a sudden, as we tried to increase our production, we found that our isomer ratio was falling outside these range. And what was happening is the cis content was going down and the trans content was going up. And that's not all to be unexpected, because thermodynamically, the E or the trans configuration is thermodynamically more favored. So anything we might do to start beating up our process, so to speak, is going to take us in that direction. So we started to do some troubleshooting. Some of the potential contributors to the off-spec product, well, these materials, again, the gossipler is a C16 molecule. It's potentially sensitive to high temperatures, and so we purify these materials by vacuum distillation. And it could be that our distillation conditions had increased in severity, and that was leading to a higher production of the trans isomer. It could be that our synthesis or our distillation might have a contaminant in it, some sort of acid component, for instance, that might catalyze the conversion of cis to trans on the double bond. Or finally, more likely, what was happening is we found that there was a drift in the tetradecatriene synthesis. And what we found is as we tried to scale up this production, the engineer who was in charge of that pilot scale production decided that in order to make more pounds of tetradecatriene, they would increase the reactor severity. But unbeknownst to them, their desire to increase productivity resulted in an erosion of isomer quality. So once we fixed that, everything came back on spec. So some lessons learned. Obviously, oftentimes your commercial product specs are the result of they introduce various process constraints. There's not just one single factor that you have to consider in order to make spec product. In our case, the quality of an intermediate stream directly impacted our ability to make final quality product. It turns out that we needed to develop some internal quality control measures in order to see whether we were making the right intermediate. That initially wasn't done. We thought that that was simply a given that our intermediate would be on spec, but it turned out not to be. And this is a classic case of where process chemistry deviations might not really show themselves until you get to bigger scale in your process, whether that's scale up in a R&D environment or all the way at a commercial environment. There are often things that don't show themselves at the lab scale. And so the process engineer really has to be aware of all the different constraints that are on the process as well as the product in order to balance those to make something that's commercially viable. A second example also from the pheromone world is what's a molecule called tricosine. And really tricosine, if you remember your organic chemistry, all this means is we have an alkene that has 23 carbons in it. It turns out this simple molecule that I've shown here with the double bond at the 9-10 position is the pheromone for the common housefly. A really deceptively simple molecule. And again, the preferred isomer at the 9 position in this case is really the cis or the Z configuration. It turns out though that an isomer mix is relatively effective as long as the Z to E ratio is above 70:30. So how do we go about making it? Well, it turns out that a chemist discovered that if you start with oleoyl alcohol, which again, this is a long molecule that has a natural origin, and we'll look at that in just a second. But in this case, this molecule is only 18 carbons long, so we're going to have to do a little work. And what we can do is with N-butyllithium and toluene sulfonyl chloride, we can start to functionalize that alcohol out at the number 1 position. But we need to build a bigger molecule. So again, looking back into the depths of your organic chemistry, perhaps you remember the Grignard coupling reaction. And in this case, we're going to take a C5 N-pentyl magnesium bromide, and over a copper catalyst, we're going to make a coupling reaction there. And I've shown the coupling bond there in green. And by adding 5 more carbons, we can magically produce our Z9 tricosine molecule. It's a pretty slick little reaction. And this one was patented here by one of the same fellows who was on that previous Gossifleur patent, Jim Byers. He came up with this synthesis, and we patented that in 1990. So again, the commercial label that we had to have from the government approved a Z to E ratio of 70/30. And all of a sudden, as we were trying to ramp up the production of this material, our isomer ratio fell below our specification without any kind of explanation. Well, we started to dig into this, and our analytical investigation suggested that we had some sort of raw material problem that was leading to the deterioration of this bond at the 9-10 position. So backing up a little bit, where does oleoyl alcohol come from? Well, this molecule that I'm showing here, this is a simple triglyceride that comes from beef tallow. And so on the left-hand side there, you can see where we've got 3 different long chain hydrocarbons that are all connected together by a glycol molecule. And this is what you typically see when you're talking about triglycerides that come either from an animal source or even from a plant source. In the case of this beef tallow, you have 2 molecules that are really stearic acid, the unsaturated portions. And then the one of interest to us is the oleic acid moiety shown at the bottom there with the single double bond. So it turns out that we can liberate that by doing some hydrogenation here, and we get oleic acid, which now is a C18 molecule. And if you remember, we're trying to get ourselves all the way to C23 with our Grignard coupling reaction. So the oleic acid is easily converted to the oleoyl alcohol. And these 2 materials are commonly found in commercial practice in things like cosmetics, where they're added because they help give a greasy or a smooth feel to creams or cosmetics. And so that's where the bulk of the use of these materials is. Commercial suppliers take beef tallow, they do the appropriate reactions to liberate these long chain molecules, and then they use them as components for the fabrication of these cosmetic materials. In our case, we're using them as a specialty chemical feedstock. So what we did is we went back to our starting material, and the first thing we had to do is develop an analytical method to determine this isomer ratio. And it turns out that trying to stick this in a chromatograph, that alcohol function is a little bit challenging, so we had to come up with a way to actually functionalize that to something more like an ether or an ester. And again, our label was prepared by a limited number of lots that we were prepared at the laboratory scale. And what we found is as we were all of a sudden producing more and more of this material, we were using multiple lots of material from our supplier. And we actually went back and found samples of those various lots. We literally went out to our drum yard and found just enough material as we drained these drums that were supposedly nearly empty so that we could do some detective work. And we found out the lot-to-lot variability at the double bond there varied all the way from 60-40 all the way up to a high of 95-5. What that allowed us to do is to go back to the commercial supplier of the oil alcohol, and we set up a program where to them, the ZE ratio made no difference. The cosmetics industry didn't care what the bond configuration was. They just wanted a long chain, partially unsaturated molecule. Well, what we did is we got the supplier to send us multiple samples of multiple lots. We were able to do the analytical work, and then finally we could on purpose purchase the lot of material that showed the greatest natural variation where the cis content was as high as possible. It actually allowed us to raise the isomer purity of our end product just by simply understanding the fact that there was natural variation on the part of the raw material in the hands of the supplier. And this really solved our final product isomer purity problem. And as I said, it allowed us to actually put out a higher purity product in the end than we actually got approved from our government label. So some lessons learned here. Well, again, once again, you may have limited lab or pilot plant data, and when you're making your product specifications, you better be careful about drawing the box too tight. You may not be able to produce to those specifications as you scale up your process. In our case, the variation in our raw material purity was not obvious when we went into our initial production, but only as we purchased multiple lots of the material was this variability apparent. And this was something the supplier really knew nothing about, because this specification really was of no interest to them for their major end use. But for our particular process, it was a key factor that we needed to pay attention to. And in our case, once again, this required some additional analytical testing development to be done in order to figure out that our raw material was on spec so that our final product could be on spec. So in this case, the bottom line is the process engineer often has to become a detective, and that's exactly what we had to do in order to chase this to ground. And of course, this applies to a variety of processes, not just specialty chemical processes. So now let's kind of jump to the other end of the spectrum, if you will, where we're moving away from looking at specific molecules to a broad range of molecules, and that's the area of crude oil processing. And so I have two more examples that come from my personal experience. And of course, with crude oil, the key characteristic isn't necessarily some particular concentration of a particular molecule, but it's really the yield versus the boiling point. And in crude oil refining, as many of you are well aware, we first attack this by simply applying atmospheric and vacuum distillation to separate the crude oil out into various fractions. And I've listed them here. And some of those are of commercial interest, and some of them, like the heavy oil and the vacuum residue, are of lesser importance, and so we might have to do some additional work. In the case of the vacuum residue, we could blend that with heavy oil to create asphalts that meet certain specifications for paving applications. Or what's commonly done is we apply additional thermal processing, oftentimes in the form of a coker, to generate additional liquids and solids that hopefully we can get back into the transportation fuel range, put in our gasoline, jet fuel, and our diesel. If physical separation and thermal processing aren't adequate, we often bring catalytic processing to bear. And so we have a whole wide variety of tools at our disposal where we're either taking light fractions and we're knitting them back together in order to get them into the gasoline or jet fuel or diesel range, or we're taking something like fluid cat cracking or hydrocracking, where we're taking the big heavy molecules and we're trying to break them apart. And again, with the goal of getting them back in the range of the major streams that we can sell for commercialization. Most of the final product streams, whether they're the result of simple fractionation or thermal or catalytic processing, are hydrotreated to remove sulfur and nitrogen. And that's been especially true over the last 30 years as the sulfur and nitrogen specs for gasoline and diesel fuel and jet fuel have dramatically decreased. So in about 2000, I mentioned the fact that in 2002, Conoco and Phillips merged together. It turns out Conoco had some heritage interests in the Canadian oil sands. And so all of a sudden that brought very heavy crudes onto the option slate for ConocoPhillips's mid-continent refineries. But some of the challenges that those Canadian oil sands crudes present are, number one, they oftentimes have a lower yield of the lighter fractions. So if you have an existing refinery that's configured for one type of crude oil, you may end up starving the light ends units in your refinery. In contrast, you may have additional heavy ends that may overwhelm your existing process units. And so all of a sudden you may have to cut charge rate to the refinery, which is generally an undesirable result. Your hydrotreating units may be challenged because these oil sands crudes oftentimes have increased levels of sulfur and nitrogen and oftentimes metals that either decrease the efficacy of your catalyst or they just potentially provide contaminants for your end products. The increased aromatics that are present in these oil sands crudes oftentimes drive your final products off spec, whether that be in the gasoline area for aromatics content, especially in areas of the country where atmospheric quality is of concern and tied to aromatics content. Or for jet fuel, you may have smoke issues or freezing point issues, or for diesel, you may not be able to make spec cetane, or you may have cold weather usability problems that we often see in what's called the cloud point test for diesel fuel. The vacuum residue that's produced from these Canadian oil sands may also be unsuitable to make asphalt just because of the heavy molecules that are present there. So just because you are able to make a vacuum residue doesn't necessarily mean you'll be able to meet all the different specifications that go into asphalt. And if you're using your coker solids in something more than just a fuel application, for instance, some coke solids are actually used nowadays to go into making specialty batteries. If all of a sudden those coke solids contain heavy metals, that can all of a sudden become problematic as well. So there's multiple challenges that materialize if you start to use some of these heavy crudes. In contrast, after we were all worked up about processing heavy crudes in about 2015, or maybe more 2013 or so, all of a sudden we had the shale crude revolution, especially in the United States. And the very opposite problem started to manifest itself, where now all of a sudden we have higher yields of light fractions, and they may make the refinery limited at the lighter end processing units. It all of a sudden may starve your heavy oil or your heavy end of the refinery. So now all of a sudden you may not be able to make as much vacuum residue as you did in the past. That may not be a problem. That may actually be desirable unless all of a sudden your refinery is servicing an asphalt market located close to the refinery. One of the unusual things that we saw several times was that the light crudes, for some reason, showed some potential incompatibility issues that would show up in the front end of the refinery in what we call the desalters. That's where you actually mix the crude with water to try and wash out undesirable salts and contaminants. And if things go wrong, you can form almost intractable emulsions or create solids precipitation challenges that can almost bring your refinery to a dead stop. So the light crudes, you might think it's simpler to process, but they introduce their own complexities. Also with the shale crudes, there's a high degree of seasonal variability because out in the field where these crudes are being produced, as you get into the winter months, all of a sudden more light ends can pass through the processing units and be stuffed into the crude oil instead of being separated off as light natural gases. And so that may mean that the crude showing up at the refinery in wintertime have a substantially higher content of light ends that may, again, bottleneck your refinery. And especially early on, prior to the development of a number of different pipelines, refineries are faced with the problems of having developed different crude oil delivery options. In many cases, we had to build rail yards that brought the crudes, and that brought its own set of limitations in terms of how the crude was handled, and also the way the quality of the crude that could be delivered because of concerns around transportation safety issues. So lessons learned from crude oil processing, you really have to go beyond yield versus boiling point. And fortunately, there are some analytical tools where crudes are analyzed, and there are some commercial products that give the refinery planners a lot of information about how the crudes divide up into the various fractions, gasoline, diesel, and jet, and also give some information about quality. But the one thing they don't tell you about is what happens when I start to apply thermal and catalytic processes to those fractions. It turns out that the light liquids that you get off a crude unit or off an FCC unit often have different characteristics depending on what the crude slate is. Crude compatibility issues often manifest themselves as well, because oftentimes a refinery doesn't process a single crude, they process a blend of crudes. So the process engineer really needs to understand where the bottlenecks are, both ahead of and downstream of their own unit, what the refinery final product specs are, and where they're most at risk, and how their unit contributes to that in a big way. Even though they may not be responsible for blending the final spec product, their unit that they're charged with operating finally oftentimes has a big impact on that. And so as new crudes are introduced into the market and potentially brought to the refinery gate, you may actually need to do some R&D work in order to tease out some of the answers to these questions. And that's in fact what happened both in the case of the Canadian crudes as well as the light shale crudes from 2000 to 2015 during the latter half of my career. So overall, lessons learned from this discussion, our commercial specs really may be set on data that we were gathered at a limited scale up mode, maybe even at the laboratory scale. And so all of a sudden, as we pursue scale up, especially of a chemical manufacturing type process, there may be new challenges that materialize that no one knew about at the lab or the pilot plant scale. And this is true across the board, and I hope that's what this discussion conveyed to you, whether we're talking about high value specialty chemicals or crude oil processing. Obviously, variations in feedstock purity or composition can impact you, and they may not be well understood. And so oftentimes it falls on the process engineer to try and dig deeper to understand those impacts. Supplier changes may not be communicated to the process engineer. The purchasing department may decide they want to secure the feedstock from a different supplier, and that may introduce a complication that isn't obvious to the person who's making that decision. And the same is true when changing crudes in a refinery. Not all the ramifications may be clear to the person making those decisions. There may need to be new analytical tests developed in order to provide the key feedstock parameters that really give the process engineer the information they need in order to run their process. So in summary, the process engineer, in my opinion, is really the key person that assimilates all the information about the process. And that goes all the way from the feedstock characteristics to the actual operating conditions of the units they're working on, and the product yields and the quality of what's coming out of their unit, whether that product coming off the unit is the final commercial product or something just on its way to becoming that. So that's where I think the process engineer brings the unique set of skills. They know about the process itself, but they also can have the tools to know about the chemistry And hopefully rolling that all together, they can be the right person to understand when things go awry, how to bring things back in line. So with that, I'll open myself for questions, and I thank you for your kind attention.
Warren, thank you so much for an incredible presentation. It was very informative, and I think it was great. So thank you. So like Warren said, now is the time to ask any questions if you have them. Don't hesitate to make any comments or ask any questions about Warren's presentation. If you're in a space and you're unable to speak at the moment, you can just type it in the chat and I'll read it out loud.
Here, I'll hold up my hand. Say thank you, Warren, for really a great presentation. I really appreciate it.
Scott, it looks like maybe your internet dropped for a second.
And is someone else seeking to ask a question, or do they just have their mic off mute and are visiting with someone else?
Yes, please. If there's anyone who has their mic on, please mute it unless you're speaking. I actually do have a question. The synthetic pheromone part was really interesting to me. And I was wondering, so you did mention that synthetic pheromones are used in insecticides, but do you know if they're used for anything else? Or?
No, what my comment was is they are regulated as if they are insecticides, but they don't actually act as killing agents. They're typically used as attractant or mating confusion elements. They're just regulated by the same federal agency that would regulate if you had something that would be a killing agent. So it's just an oddity, because you'd think that pheromones would be so benign that there wouldn't be much oversight, but in fact there is. They're regulated by the same federal agency that would regulate a hard insecticide.
Wow, that's very interesting. Yeah, thank you for clearing that up for me.
Sure.
Oh, there's a question in the chat. How did you manage to have all these feed variations not impact your final product? Did you have to work with ops engineers in the front end or of refining, crude unit, etc., to make sure you were not impacted at the chemical plant? This is by Rajan.
Okay, so someone still has their mic unmuted, I'm afraid.
Yes, let me see if I can see if there's someone in the audience that has their mic unmuted. Oh.
Okay, maybe.
Oh, Mirza, I'm sorry, Mirza, would you mind muting your
right.
microphone?
It's not muted. It's open, yeah.
Thank you.
You want to say something?
No, we were just hearing background conversations.
Yeah, there's a bit of background noise.
I don't know if that's occurring at your location or elsewhere. Everyone else is showing their screen is muted. So, okay, to your question, or to the question in relation to specifically crude oil variations, I alluded to the fact that some R&D work might be needed, and that's in fact what happened in the case, especially of the heavy Canadian crudes, is the refinery recognized that they were going to have a dramatic shift in the yield and the quality of their various streams. And so we set about a very wide-ranging R&D program where we brought in heavy Canadian crudes, and we literally duplicated what would happen in a refinery in the R&D environment. We fractionated it, and we subjected many of the fractionated streams to catalytic processing, and then did detail analytical work to characterize and say, well, you know, if you make a diesel stream from this particular cut, it's going to have these sort of cetane characteristics or cloud point characteristics, and it's going to potentially drive you off spec. So you can only, for instance, you may only be able to charge 20% of your refinery charge may be Canadian crudes, and the remaining 80% may need to be more traditional conventional crudes in order to not drive the entire refinery off spec.
Yeah, Warren, I remember when we did that work, and we heard from one refinery operations guy that hey, this R&D might be better than guessing. So
Yeah, That was the quote. R&D, it's better than guessing, and we almost decided to print that on T-shirts as our logo. But
Well, I
nonetheless,
view that as high praise.
yes, coming from the refinery ops folks, we felt like it was a positive feedback loop coming to us, basically saying without the work that we had done, they would have been operating blind, and if they would have just charged in and started putting these heavy Canadian crudes into their refinery, they would have been in a world of hurt. In some cases, back to the previous question that came in on the chat, it meant that we had to invest in additional capital to provide additional hydrotreating capacity in order to get the materials to be able to make spec product. So there was kind of this feedback loop of having open questions, doing R&D work, gathering the information, and then figuring out what do we needed to do from a capital investment standpoint in order to take advantage of these crudes, which were typically available at a depressed price in the marketplace.
Thank you. Are there any other questions from anyone?
Yes, can I say something?
Yes.
The presentation was excellent, very good presentation. But I have a different question, that crude oil is discovered in different parts of the world, maybe in the Indian Ocean or Bay of Bengal, and the impurities in the crude may be different. So there is to determine the impurities and how to rectify these impurities. And it was told that R&D has a very big role to play. So there are many impurities. So impurities like phosphate, phosphatides, then free acids, gummy substance, color bodies, hydrocarbons, ketones, aldehydes, sulfur, all these things. Maybe there are other things in the impurities. And handling of this crude is a very big problem, this to get rid of the impurities. So what is your suggestion?
Well, as you alluded to, oftentimes you may need to do some R&D work. And one of the challenges is that the number of integrated oil companies or even just downstream oil companies that have R&D facilities at their immediate disposal has dwindled dramatically over the past 40 years, as we all know. And so you may be forced to go to some outside commercial lab that will do some sort of crude characterization for you. The real challenge is oftentimes it's more than just the characterization. It sounds like you've already have access to a characterization analysis. The trick is where do you go to actually have somebody that has small scale processing units where you can put these crudes in, fractionate them, take the various cuts, and then actually further process them. Because as I tried to highlight, making refinery spec product is a lot more than simply fractionating the material and taking the naturally occurring distribution. There's thermal processing, there's catalytic processing, and without doing testing on some of those types of units, you really don't know how the catalysts are going to hold up, whether they're going to deteriorate in terms of their performance, or how effective they'll be at doing the hydroprocessing functions that are often applied to get rid of those contaminants. So it is a challenging issue and question just because of the dwindling resources there are out there to get unbiased R&D information about these novel crudes. And you really don't want to turn your refinery into a test unit, although I suspect that's often happening these days because people don't have access to a lot of R&D resources, or it's considered too expensive to try and pursue that.
If I can add something, this is Marty Gonzalez with BP. There's quite a bit of literature out there on the impact of different contaminants. And for example, I think Springer Handbook of Petroleum Technology just probably 2 years ago has a really good chapter on on heavy Canadian crudes and the contaminants and how you adapt to those. But really, it's yeah. So depending on the type of contaminant and where it comes out in the crude, you're going to have a different type of impact, particularly in the area of catalysts and hydroprocessing catalysts. There's, the vendors have developed all kinds of special stuff that they want to sell you to trap things like arsenic, or, on the heavy end, you have nickel and vanadium. And there's information about the chemical structures. A lot of these are locked in like porphyrin rings. And so there's a pretty good basis to start from if you have questions. And then all the forums that you have, NPRA, what do they call it? AFPM now. You shouldn't have to do a lot of your research from scratch. Sometimes you run to these oddballs, or sometimes they're trade secrets, like you mentioned, phosphates. That one tends to be particularly mysterious because sometimes it's added in production chemicals, and you're not really sure when you're getting something like that. And the Canadian stuff can be like a mishmash of different things. It's not sometimes just one crude, or it's too heavy, so they'll blend it with the synthetic portion. But once you're informed about those things, I think that there's been a lot of research done.
Thanks for sharing that, Marty.
Yep.
I would be remiss if I didn't mention there's an organization called the Canadian Crude Quality Technical Association, the CCQTA, and they hold technical meetings that address a lot of what you're saying, and that's where a lot of the information has come out into the more public domain about how refiners over the past 20 years have adapted to the presence of these new crudes in the marketplace. So your point is well taken.
And they publish assays, right, that are openly available on the internet that you can go look at.
Yeah. The assay information is great, but it doesn't really give you all the information about what happens when you put some of those streams into processing units, thermal or catalytic. That's sort of a second generation. You can get the first picture about what the natural yield diesel looks like, but it doesn't tell you, for instance, what the diesel range material coming off your FCC unit or your hydrocracker looks like. That's a little more challenging information to garnish out of the open literature.
Yeah, and there are things like total acid number, where all things are not created equal. Asphaltenes are not just one type of molecule. Yeah, so that's a good point.
Yes.
Thanks, Warren.
Thank you for sharing that.
Thank you so much, everyone. I think there's one more question that Rajan posted to the chat. He says, great presentation, thanks. With refineries driven by crude prices, was there enough driver from R&D to push refineries to make these changes? i.e., was specialty chemical profits enough to push refineries to make these changes?
Well, again, for the crude oil examples that I listed, especially the one about Canadian crudes, there was definitely, our work was motivated by a direct request from one of our mid-continent refineries that was going to substantially increase their charge rate of the Canadian crudes. And so in that case, we did the research and they made the capital investments. The research was specifically targeted to guide them as to how much capital investment they had to make in order to make the crude slate switch. And so I guess the bottom line answer is yes, the R&D information was a driver to specifically result in invested dollars in the refinery so they could effectively and productively make that crude slate switch.
Great.
I might just as a footnote comment about the AgriSense joint venture with Dow Corning. It turns out that the early 90s were not kind to the refining industry, and Dow Corning at the time found themselves in their own quagmire with their silicone breast implant business. And it turns out, unfortunately, by 1993, the AgriSense joint venture dissolved and the pheromone technology was sold to a third party. So unfortunately, that went on its way, and it wasn't considered a big enough core business for Phillips Petroleum to pay attention to. But in terms of my career, it was an interesting 5-year interlude into some high-value specialty chemistry that I found fascinating personally.
All right, everyone, thank you so much for a great discussion. I just wanted to take a few minutes to talk about the upcoming PEP Talks. Warren, thank you again for a very interesting presentation. I will share my screen now. 1 second. Sorry, bear with me. I'm trying to. Sometimes these things can be pretty finicky. All right, I have it now. Okay. Can everyone see my screen?
Yes.
Okay.
Yes.
So we have two upcoming pep talks. The next one next month on September 8th will be about the role of the process engineer in enabling effective technology development. And Dale Kearns will be leading that. He is from Deloitte. He has over 40 years of experience in industry consulting, teaching, and service through professional society initiatives. In October, we have the pep talk that was originally scheduled for today. Pete Kramer, who is Chief Supply Chain Officer at AB InBev. He'll be providing an overview of the exciting beer industry. So hopefully you all can attend that. And I will talk briefly about the community. So the community website, you can access it easily by going to aiche.org/process engineers. And if you need any more information or if you have any questions, you can email either me at dennyb@aiche.org or Michelle. And another way of actually going to the community from the AIChE homepage is from the top navigation bar. You can click on communities and you'll find the communities of process engineers and that drop down right to the right. So, all right. Again, I want to thank Warren for leading a great talk and thank you to everyone who attended. I hope you all can attend the next talk. And definitely please spread the word about these talks to other process engineers who might be interested. And I'll briefly turn it over to Scott to wrap things up.
I'll just remind everyone that this excellent talk was recorded and you can access it at the link that Danica showed. So tell your friends if you enjoyed this presentation, tell your friends to check out the link on the AIChE website and share that with others. And you can do the same with the other pep talks as well. So thank you very much for attending. I certainly enjoyed it and I enjoyed the discussion.
Thank you, everyone.
So much. Thank you.
Bye-bye.
Bye. Thank you.
Thanks, everybody. Thanks, Warren.